Okay, so thanks everyone for tuning in for the second Quantum Gravity and Information virtual seminar. Today we're very happy to have Tom Faulkner, who's going to tell us about his work on canonical purification for the entanglement wedge cross-section. Tom, thank you very much, and the floor is yours.
Okay, well, thank you very much for having me, and this is a great idea to have these online seminars, so I encourage that. So I'm going to be talking about work that I did with, oh yeah, and please interrupt. It's kind of a strange thing to talk into the void and to not have any responses or anything, so please interrupt. Yeah, so I'm going to be talking about work with my student Shovik Dutta in this paper here. And the basic idea is that we came up with a new duality for the entanglement wedge cross-section. So the entanglement wedge cross-section is some quantity, some new geometric quantity that is defined using entanglement wedges. And the summary is essentially the entanglement wedge. Here's a picture of the entanglement wedge for two regions in ADS3, where the two regions are A and B. The entanglement wedge in this case is non-trivial. It connects A and B. And the idea is that there's a sort of canonical purification that you can construct with that entanglement wedge, essentially by taking two of the wedges and gluing them together. And then you look for entangling surfaces in that glued geometry. And with that, you can find entangling surfaces that map out the entanglement wedge cross-section. And so that's what most of the talk will be about. At the end, I'll give some sort of speculative ideas of trying to connect this to something called the split property in quantum field theory. I should also say that the entanglement wedge cross-section was defined in a series of papers from 2017, where they conjectured a duality with something called the entanglement of purification. And there's also another conjecture for duality between the entanglement wedge cross-section and something in the boundary theory by Tamayoka. The starting point is to think about just purifications in general. So if I have some mixed state, so I have some density matrix rho, then perhaps it came. It was a mixed state because it came from entanglement with some environment. So we had some pure state on some larger system, which includes the environment, and then we trace over the environment and we get a mixed state. Such a pure state psi is called a purification. And it need not be that the state in question came from entanglement. Maybe it just came from sort of classical ignorance or some classical probability distribution, but you can always find purifications. And in fact, there are many purifications. For example, just in the example here, I can take a unitary and act on the environment, and it still gives me a valid purification of the original density matrix. Now, it turns out that there's a special purification, and it comes with it's called various things. You might know it as the GNS state, or you might know it as the Sommerfeld double. So let me describe that now. And I'm actually going to describe it in a slightly strange way. So maybe this is not very familiar from the way that I'm describing it. It's the way that I guess I think about it essentially because it makes it clear that this purification that I'm going to talk about is canonical. All right, so the idea is to consider a new Hilbert space. So given the Hilbert space H that we're working with, so the density matrix rho is a density matrix on H. The idea is to consider a new Hilbert space, which is just the space of matrices that act on that Hilbert space. So for now, let's just take the Hilbert space to be finite dimensional, and then all operators on the Hilbert space are just matrices, and you can think of that as endomorphisms of H, maps from H to H. Okay, but actually this space you can think of, is a perfectly well-defined Hilbert space. So in particular, we take states in the Hilbert space, which you maybe thought of as vectors, and now they're matrices. So matrices are now vectors in the Hilbert space, in this enlarged Hilbert space. And I need to specify an inner product. And the inner product here is just this, so between two matrices M1 and M2 is just trace M1 dagger M2. And there's a basis that I can pick by just picking a basis in the original Hilbert space H and constructing IJ, as I've denoted here. And from this, it's pretty clear that this new Hilbert space is a doubling of the old Hilbert space, where you can think of it as a tensor product of H with a complex conjugate of H. Now in this new Hilbert space, this doubled Hilbert space, we can think about purifications. And in fact, there's a simple purification of the original rho on H, which is just to take the square root of rho and think of that as a matrix in this Hilbert space, so a vector in the Hilbert space, that is. So in particular, you can take rho, square root of rho as a vector, and then you can trace over H star, and you'll see when you do that you'll get back to the density matrix rho. That's what it means to be a purification. Perhaps an easier way to see why it's a purification is just to think about observables on the larger Hilbert space. So there's sort of two kinds of observables on the larger Hilbert space. There's operators that act on H, and there's operators that act on H star. Is there?
Oh yes. Oh, sorry. I'm trying to get work. I think we have a question here in Amsterdam.
Okay, great.
Hi, Tom. This is Eric. I have a question. I thought that in the GNS construction, the state also entered in the definition of the inner product.
I missed that. I missed that.
In the GNS construction,
yes,
the state enters into the definition of the inner product.
The space,
The state.
Yeah.
Actually, part of the definition of the inner product. I don't see that in your slide.
Right. So take the state to be the unit operator, and then it's that.
But it is unit identity operator. I agree.
Yeah, the identity on the larger Hilbert space. So yeah, that's right. So you can also describe it as square root of rho is your state, and then the GNS is really what you get by acting with operators on the left of the square root of rho. But yeah, just take the unit operator.
Okay. Then I agree.
So did that answer your question?
Yes, but since you did seem to be talking about a general state rho,
Yeah.
that rho should have entered into the definition of the inner product of M1 and 2.
Uh-huh.
And since you've written it like with the identity there, you seem to be talking only about the density matrix that's proportional to the identity.
Say it again, sorry.
So generally, in the GNS construction, you start from a state,
Uh-huh.
and then the state defines also the inner product.
Yeah, that's right. Yeah, I mean, you can describe this with a slightly different inner product. But what I'm doing is I'm starting with an inner product related to a state, which is the unit operator, and then I'm describing it in terms of that. But in finite dimensions, there's no distinction between these things. It's not important. Of course, in infinite dimensions, there's a big distinction, and you should be careful. Yeah. Yeah. Good. So yeah, that's right. Now, okay. So the purification that we're talking about is now just the square root of rho, and one way to see that is to think about the operators that are acting, and there's operators that act on H, which in terms of this matrix representation of the Hilbert space are just operators that act on the left. And the operators that act on H star are operators that act on the right of the matrix. So that means I can take expectation values of the operators on H. That just gives me a left action over here. which then just using this inner product just gives me trace rho O. And so I just get the expectation value of O in the state rho. And so indeed, this purification has the same expectation values of operators in H as rho. And so that is another definition of a purification. Right? So if all the observables in H are the same, then it has to have the same reduced density matrix. Okay. Good. So there's another way, perhaps more familiar way of describing this. So right. So which relies on the existence of an anti-linear operator T, which acts on H. Okay. And so given that, I can define an isomorphism between this doubled Hilbert space that I just described, H tensor H star, and just a tensor product of H with itself. Okay, and it's defined in this way, say on this basis, Eij. And then if I take that and I act on this purification, then what do I get? Well, I get this this object here, which is essentially the thermophile double. In particular, if I take my basis, to be eigenvectors of the reduced density matrix, then it looks exactly like the thermophile double. Of course, often when you talk about the thermophile double, it's in the context of an actual thermal state, where the density matrix is given by e to the minus beta h, where h is a Hamiltonian, and then the i's are just the energy eigenstates. The point here is that this is a general idea. You can always do this. And the point of working in this other Hilbert space, which is not H tensor H, but H tensor H star, is to make it clear that the choice is canonical. So in this other description, you have to define this anti-linear operator T, and that's a choice. So it depends on that choice. It doesn't depend very heavily on that choice. If T acts locally, if your Hilbert space has some local structure, for example, it's the tensor product of various things, A and B, where A and B are related to different localized regions, then if T acts locally on those two, then it won't affect this discussion at all. So any T which acts locally will give the same result as what I'm going to talk about. Okay, so in this context, we can define this thing called that I'll call the reflected entropy. It's just the name that we chose for this. So we take the original Hilbert space in this discussion to be a tensor product of A and B. So A and B are just some subsystems in your Hilbert space, and then the density matrix is rho AB. So that's just a redefinition of what I'm talking about. And so now we're talking about sort of mixed states. Rho AB is a mixed state on a bipartite Hilbert space. And so the canonical double is just the square root of rho AB. And that lives in this doubled Hilbert space, which is now HAB tensor HA star B star. And in that context, now I can just think about an entropy. So I'll call this SRAB. So it depends on A and B in a canonical way, because this construction is canonical, but I'll define it as the Von-Neumann entropy of rho AA star, okay? So because it's a purification, it's equal to the Von-Neumann entropy of rho BB star, so there's no distinction between A and B. So it's symmetric between A and B. Okay, very good. And so I claim that this is sort of an interesting correlation measure between the two systems, A and B, so in the state. So why is that? Well, you can prove various things about SR. You can prove that it's bigger than the mutual information and less than the minimum of just the entanglement entropies of A and B. And you do that, using sort of well-known entropy inequalities like strong subadditivity and so forth. And then, this teaches you that if SR vanishes, it vanishes if and only if rho AB is rho A tensor rho B. So, you know, that the first indication that it's some kind of correlation measure, because, you know, it vanishes if it's just this factorized density matrix. Now, it's not, maybe not really a correlation measure, so I would like it to be, but for that to be the case, it should be monotonic under increasing the region. So if I had AB and then I added a little bit C, then this SR should increase. And you know, if it was a real correlation measure, then it has to increase. And actually, we haven't managed to prove this. We haven't found any counterexamples to this, and we have found a proof of this monotonicity for the integer Renyi entropies. So if you define this reflected entropy in terms of the Renyi entropies, like trace row AA star to the n, instead of, you know, trace row AA star log row AA star, then the integer Renyi entropies satisfy this monotonicity statement. But you can't actually go from some statement about integers, some inequality on the integers to an inequality away from the integers. So that's not a proof. Okay. Now, another reason to think that it might be related to a correlation measure is that it's related to another correlation measure, which is this entanglement of purification. So this is another thing that people put forward as a duality for the entanglement wedge cross-section, and as I'll discuss, SR is going to be dual to actually twice the entanglement wedge cross-section. So, you know, the entanglement purification is basically what I've set up. You take any purification, not necessarily this canonical one, in this enlarged Hilbert space, ABE, and then you split E in all possible ways into little a and little b, and then you compute the Von-Neumann entropy of big A, little a. So that's like AA star. And because SR is an example of one of these, and we're minimizing, that means that the entanglement purification has to be always less than SR. Okay. So now we've set up these quantities. We've set up this canonical purification, and we've set up this reflected entropy. We'd like to know how to calculate it in ADS-CFT. And so that's what I'm going to discuss now. So basically, let me just give you a
quick question.
Yeah.
How easy is it to build a state that is strictly smaller than has an entanglement of purification that's smaller than SR?
You can do it. Yeah, that's not so bad. You can do that.
You can do it easily.
You take a few qubit system and try to do it, and indeed you can. There's a question about whether you can get lower than SR over 2. I have a conjecture that it's always bounded by SR over 2, and that will be important later. Well, I mean, it won't be important, but I'll mention that later again. Okay. But actually, it's pretty hard to get much smaller than SR just playing around with, you know, small qubit systems, and yeah. Okay, but you can do it. Okay, so now, okay, so we're just going to give you a picture, and this is not a proof. This is just a picture. So the idea is, you know, AB, the reduced density matrix row AB, is somehow tied with the entanglement wedge of AB. So let's think about a situation where the entanglement wedge is non-trivial. If the entanglement wedge is trivial, as in it's, you know, as in if A and B are disjoint, then it could be the entanglement wedge is trivial. It's just a sum of 2 entanglement wedges for A and B, in which case all of the quantities that I'm going to discuss are 0 to leading order in G Newton. So let's take it to be non-trivial. Then we have this sort of non-trivial connection between A and B. And the idea is to start with that entanglement wedge, essentially to throw out the extra pieces. So the E is the environment here, which are just the extra pieces that are, you know, AB complement, if you like. And you throw that out, you just have the entanglement wedge, and you take 2 copies of the entanglement wedge and you glue them together along the RT surface. And to draw pictures, it's convenient just to put them on top of each other. So that's what I'm going to draw. I have one wedge on the top and another wedge on the bottom. They're glued on the RT surfaces. And there's some prescription for how you go through that gluing, right? So this is I claim this is a picture of this, this doubled Hilbert space. So where I have A, B on, the boundary of the entanglement wedge is the Hilbert space of the boundary quantum field theory. And in this case, we have HB from the original wedge, and we have HA star, B star from the sort of the glued wedge, which is on the bottom side. It lives on the back side. Okay, so when you do this gluing, you have to specify, what happens when you go through the RT surface. Well, the rule is some kind of reflection boundary condition. So as you go in, you should reflect back along the RT surface. In reality, the real construction of this involves a space-time gluing. So there's time here. So I'm not drawing time. I'm just drawing a single time slice of ADS. But now, if I include time, then I have to tell you how to glue the entanglement wedges in time. So in particular, so I was sort of using this language where the entanglement wedge is this spatial region that lives between the RT surface and AB. But you can also think of the entanglement wedge as the domain of dependence of that spatial region, and that's some space-time region. And then I should tell you how to glue those two space-time regions. So that's really what's happening at the RT surface. So if I zoom into the RT surface here, in real time what I have is two wedges and I'm gluing them together. And to do that, I need to apply some CPT conjugate. And that's what I really mean by this reflection boundary condition. As I go in, I come out on the other side, and because I'm drawing the picture where the entanglement wedges are on top of each other, it has the effect of a reflection. Okay. And so then the idea is that this is the construction and it works in real time, but you should also probably solve Einstein's equations to the future of the RT surface. And once you've done that, after patching these together, then that is meant to be the dual of this purification. And this construction is due to Engelhard and Wall, actually. They showed how you can take an entanglement wedge and glue it to its CPT conjugate. And so that's essentially what we're using here. And yeah, so that's the dual of that density matrix. And then all we have to do is calculate entanglement entropy in that new spacetime using this HRT formula, the usual formula. And so, what you find is that because there's these sort of funny regions, which I've denoted with the question mark in this picture, there are regions that are to the future of the RT surface. And in principle, we could figure them out by solving Einstein's equations. But in practice, we don't know what they are. So what we want is to find things that don't care about that region, that don't probe that region. And so if I ask questions about entanglement entropies that are somehow reflection symmetric, as in, I take some region on the original entanglement wedge, and I take the same region on the glued entanglement wedge, then what you'll find is that the RT surface actually never goes into these question mark regions just by that symmetry constraint. It has to pass through exactly through the RT surface of the AB, so the AB RT surface.
Question?
Yes.
So in this gluing, where did you take the square root of the density matrix? So it's.
So I haven't. Yeah, that's kind of what I haven't really explained how this happened. I'm just giving you a prescription. But you have to take the square root of the density matrix, because otherwise, if you don't do that, then let's say I just took the density matrix, then the bulk dual will be much more complicated. It'll be very different to this. So that'll come out from the discussion when I just discuss how to show this. But yeah, it's important. Yeah. Okay, so okay, so if we pick symmetric boundary regions, then the IT surface, passes, doesn't enter into these weird regions. And an example of that is exactly this reflected entropy, which is the density, which is now the entanglement entropy in this state of AA star. So AA star in this case, AA star is now, because of the gluing of the IT surface, it's now a closed region on the boundary. So it's a closed surface on the boundary, and in particular, you can see that it's going to be homologous to this blue region that I've drawn here, in the glued space, right? In that notion of homology, and the minimal entangling surface will define this entanglement wedge cross section. So it will fall down into the bulk, and it will settle at the minimal cross section. And so you find that the Von-Neumann entropy of AA star is computing this cross section. Okay, so indeed, this is the entanglement wedge cross section. The entanglement wedge cross section, well, it's actually twice the entanglement wedge cross section, because you had the blue surface and the dotted blue surface for the glued entanglement wedge. And usually the entanglement wedge cross section was how it was originally defined in those papers that I mentioned before. What is as follows: you take the minimal surface MAB, which are these sort of small semicircles that fall into the bulk here, and you split them in some way into two regions, gamma A and gamma B. And then you find a minimal surface that's homologous to A union gamma A, so that's that blue curve here. Although I guess I haven't really drawn the minimal surface, but you find the actual minimal surface there, and then you minimize over all possible splittings gamma A. And it's not too hard to see that that's the same. That gives you the same surface as this gluing procedure gives you. Of course, the gluing procedure then gives you this extra factor of 2 because you have the two wedges. Okay, and it works in a more general setting. In more general settings, for example, the original way that we were thinking about this, which made it a little bit more clear, this duality, at least to us, was when A and B actually share a boundary, right? So I've drawn a picture of that here. So I've just included a little bit of B in the left region, and in that case, what you find is this entanglement wedge cross section comes to the boundary, right? So it's boundary anchored now, yeah, I mean that's what it is. This is the minimal surface associated to AA star that will compute the entropy of AA star. But it also happens to be the entanglement wedge cross section as I defined on the previous slides. And the surfaces here, the ones near the boundary that come up near the boundary, the blue surfaces, they look like these reflected geodesics that we studied in a previous paper, using a seemingly unrelated modular theory, and it turns out that there is an intimate relation between that and these reflected minimal surfaces, and that was one way of proving this duality. I'm not actually going to talk much about that way. It also works if there's a black hole in the middle of your wedge, and this is the reflected minimal surface in that case. Okay, let's compare a little to the entanglement of purification conjecture. So the conjecture was that EP, remember, after minimizing over all possible purification and all splits of E of the environment, then the original conjecture was that should be equal to the entanglement wedge cross section. It turns out that this is actually not inconsistent with our duality, because I told you EP, because SR is an example of a purification, it has to be less than SR, But SR, I'm claiming, is twice the entanglement wedge. So there's this factor of 2 here, which is important. Entanglement wedge cross-section. And so it's possible that upon minimization, EP, you essentially get this factor of 2, or a half, if you like. So you start out at SR, and you minimize, and then you get a factor of 1/2 of SR. And then that would be, these dualities would be consistent with each other. So indeed, in very simple qubit systems, you can show that SR is not equal to 2EP, which would have to be the case if this duality was to be, if both of these dualities were to be correct. But perhaps it's, qubit systems are not holographic theories, so maybe it's true for holographic states at leading order in G Newton or something. I think that conjecture is still open. There have been various attempts at proofs. So one thing that I should have probably mentioned before, but now I'm mentioning it now, is that there's a really simple example of this, which is the thermal field double itself. If I take, the Gibbs state and I think about the canonical purification, it's the thermal field double, and of course we know what the dual of the thermal field double. It's just the eternal black hole, where you have two CFTs, a left and right CFT. So now if I take AB to be the entire left CFT, so A union B is the full left CFT, then the entanglement wedge is just the left exterior of the black hole. But now, I split the left into AB. Then, you can ask, what is the entanglement wedge cross-section in that case, as per the definition of splitting the minimal surface. In this case, the minimal surface is just the horizon of the black hole, and minimizing over all splits. And what you'll find is that you'll get this blue curve that goes from the boundary between A and B to the horizon. And in our language, this reflected entanglement entropy is where I just take the reflected regions on the right CFT, A star and B star, and I find an entangling surface that goes that computes SAA star, and in that case the reflected minimal surface just goes through the horizon, and indeed it's it gives you twice this cross section. So this is essentially a trivial example because we know how to calculate entanglement entropy in the thermal field double, where you have regions on the left and the right. Essentially it's a trivial consequence of the RT formula in that case. So one way of thinking of what we did is just generalizing this local case to more general density matrices. And what I mean by local is that the density matrix itself is e to the minus beta h, where h is the Hamiltonian, which is some integral over some local object. So there are several cases where your density matrix is local in that sense, and in those cases, our duality is just a trivial consequence of what's already known about the RT formula, and what we're doing is just generalizing it to the non-local case. Okay, hopefully that's somewhat clear. Okay, so let me sketch a few of the proofs that we gave for this duality. So I've already mentioned one of the ideas, which is to use this Engelhardt wall construction. They showed in pretty, it wasn't the trivial work, how you could take an entanglement wedge and glue it to its CPT conjugate. Actually, they showed many more things in this paper there were two papers actually, and this was just one aspect of their construction. They showed that it was possible to do this, and so you could read our result is just using that construction and computing entangling surfaces in that construction. In particular, entangling surfaces that have this symmetry property. They indeed, in the paper, they suggested that the dual of this construction was the GNS state, which I'm thinking of as the square root of the density matrix. And important for their gluing construction was that the surface that you're gluing across is an extremal surface. So it's one where the expansion vanishes, the null expansions vanish in both null directions. Theta plus minus vanishes. If that didn't vanish when you do the gluing, you'll actually get a pretty bad singularity, or if you like, you'll get a shock wave which has to be sourced by matter. However, when you do glue across an extremal surface, you still get some kind of singularities. In particular, it leads to some kind of discontinuous shear, which you can interpret as a gravitational shock wave. This is not a huge problem for the construction. The solution still exists. You can still solve Einstein's equations into the future of the minimal surface. Okay, and then as I said, we just find HRT surfaces in this new spacetime. We actually gave other proofs. So another proof, which is actually kind of related to this, is we gave a path integral construction. And the idea was to do some replica trick on steroids, where instead of thinking about this canonical purification, which is the square root of rho AB, we think about rho AB to some power. So let me take that power to be m over 2, and let me take m to be an even integer. Then if I normalize it, then this is what I get, the state here. It's like this. It's like this canonical purification. Of course, it's not a purification at all anymore. But it's just a state that you can write down in this double tilted space, a pure state. And then you can calculate, entanglement entropy associated that state, and let's just calculate the Renyi entropies of AA star. So we have two numbers, m and n. M was the original definition of the state, rho EB to some power, and n is the Renyi index. And so the idea is that in quantum field theory, we can write down path integrals that compute this for integer n and even integer m. That's when you essentially get integer powers of the density matrices. And then if we can do that for enough n and m, then maybe we can analytically continue. And what we're really interested in is some limit where we take m and n to 1. Now, actually, it turns out that we didn't emphasize this in the paper, but there's a slight there's a delicate order of limits that you need to take. You need to take n to 1 first, and then m to 1. And this is a subtlety in this duality, and this was pointed out in this paper that I've referenced at the bottom here. Okay, but that's the basic idea, and then right. So that's just a quantum field theory statement. Actually, we could just do that in quantum field theory. But now the idea is to use ADS-CFT to construct the solutions, bulk solutions that calculate those Renyi, this sort of generalized Renyi entropies with two integers n and m. So let me give a slide. I try to give a picture of how that works. Okay, so let's try to actually construct the state rho AB to the m over 2, where m is an even integer. To do it, let's consider the original Lefkowitz-Moldesina construction of which calculates the entanglement entropy of AB, as an intermediate step, it calculates the Renyi entropies of rho AB. So it's calculating trace rho AB to the m. Okay, so this is some partition function of the CFT on some manifold MM, which is some branched cover of the original space. I'm not going to go into details, but yeah, you can write down what MM is explicitly, and then using ADS-CFT dictionary, then that should be that partition function should be calculated by some gravitational action for some solution where BM is some Euclidean solution in the bulk to Einstein's equations that limits to Mn on the boundary, at least schematically. Okay, and the CFT partition function on MM is the thing that calculates the, is the M replicated space that computes the powers of the density matrix rho AB. So trace rho AB to the M. So we're not getting the reflected entropy or anything like that now. This is just the standard Renyi entropies for AB, where my parameter is M. So let's draw the cartoon of BM, the bulk solution. Well, the idea is let's just draw it's just a cartoon. Let's just draw a two-dimensional slice through the bulk space where the two-dimensional slice comes up to the boundary and slices the boundary along a one-dimensional slice. And that one-dimensional slice sort of goes around the entangling surface on the boundary. So on the boundary we have, so in the case M is equal to 4, I have 4 copies of the theory on the boundary because I'm going around the entangling surface. I did the replicate trick, so I have I have the usual thing where I have the 4 copies. And then in the bulk, it sort of smoothly caps off, and it caps off at some point, which is a point of symmetry, which is where the RT surface will eventually sit once you send M to 1. Once you analytically continue and send M to 1. Okay, so this is the bulk spacetime, a cartoon at least. I've drawn an extra symmetry in this spacetime, there's an extra symmetry where I'm assuming that the boundary theory, the original state that I'm interested in, has some kind of Euclidean time symmetry. So if I consider the state that's produced by a path integral, and it has some Euclidean time reflection symmetry, then that will, the bulk solution will inherit that symmetry, and that's that symmetry of a flipping across this dashed line here. Good. So now given Bm, right? So this Bm, the partition function of this computes trace rho AB to the M. But now this bulk spacetime has a symmetry. It has a symmetry where where I just flip the solution like this, okay? So let me think of that as some kind of time symmetric slice, and there's some Euclidean time symmetry. And I can think of that as the inner product of 2 states. So trace rho AB to the M, I can write as the inner product of rho AB to the M over 2, rho AB to the M over 2 in this doubled Hilbert space, like that. And so it doesn't take much of a leap to see that this path integral is computing that overlap. And if I just take half of this path integral, I'm computing the state. So that computes the state rho AB to the M over 2. Or at least that's the bulk dual of that state. And once you have it, you can evolve in real time as usual. And then in real time, you'll get something that's sort of a generalization of this Engelhardt wall construction, where you're gluing together 2 entanglement wedges, but those which are essentially RAB and RAB star in this picture. But those entanglement wedges are different to the original entanglement wedges because they come from this replicated bulk space. Okay, and so in this we can calculate entanglement entropy, we can calculate Renyi entropies, that's much harder, but the Von-Neumann entropy is just RT surfaces in this space. So we can take the limit n to 1 first, which was the right way to do it, and then m, and then we'll try to analytically continue m. So right now m is an even integer. We haven't continued m, but n we can take to 1, and it's just computing entanglement entropy, von Neumann entropies, which is then just using RT surfaces in this space. In particular, because we have this time reflection symmetry, we can just look at RT surfaces that live on this time slice here. The M analytic continuation is actually quite straightforward now. All you need to do is understand, what should I replace one of these wedges with when M is not an integer. So that's a prescription that Lefkowitz and Moldacina wrote down, which is you think about this quotient, you take Bm and you quotient it by Zm, and then you can define that away from integer M, that quotient. And then the idea is to take two of those wedges and use just the entanglement wedge of 2 of them and glue them together. And because the gluing construction only really locally depends on what's going on this time slice, on this top time slice, it doesn't really matter what's going down here. So I can think of gluing in m over 2 copies or m over 2 minus 2 replicas where m doesn't need to be an integer anymore. And then and for example, I can also solve to the future in real time, and that will give me a construction of that space where m is not an integer. You can also do quantum corrections. Actually, that's fine. You have to think a little bit about let's say one loop corrections to the path integral on this conical space, or really the density matrix. You get a density matrix, a bulk density matrix for path integrals on this conical space, and then you can define the mth version where m is not an integer just by taking powers of that density matrix in the bulk. And at the end of the day, when you take m to 1, what you're actually going to get is the quantum corrections are governed by basically bulk entanglement, as is the usual case for the RT formula, but now it's in a particular state where the state is the bulk GNS state. So this square root rho, but now in the bulk. Okay, so now, so now we have analytic continuation in M. We can take M to 1. When you take M to 1, these entanglement wedges, RAB and RAB star, just go to the original entanglement wedges of the original spacetime. And so then you get this gluing construction. Of course, as M goes to 1, I'm describing rho AB to the 1/2. So that's where this 1/2 comes from. Okay. All right, so that was one proof. There's other proofs that we gave. You can describe things using modular theory. You can describe this this reflected entropy, this NM reflected entropy that I defined using modular operators, and then you get this notion of reflected geodesics, which we studied before, and it exactly looks like the entanglement wedge cross section. You can also write down twist operators. They're a bit more complicated than usual because you now replicate twice. You have NM, so now your twist operators are, not just cyclic permutations, but they do other funny things. But you can write them down, and you can compute in 2D. You can quite explicitly compute things, say at large C, using blocks, or some vacuum dominance assumption, and you find exactly the same answer as ADS CFT and ADS 3. So I think there's strong evidence for this duality. And so what I'm going to move on for the last part of this talk is just a possible application to something called the split property. Okay, maybe I should ask if there's questions right now. Pause for questions. Okay. How long should I pause for? Okay, let's move on. Okay, so let me describe quite schematically the split property. So this is this is a property of quantum field theory. You might think of it as a constraint on quantum field theory, but I think most of the quantum field theories that you guys would think about satisfy the split property. And it's a strong form of locality. So it's a way to build in some stronger notion of locality into the algebraic formulation of quantum field theory. So one way of thinking about it is if I have some regions A and B, and B is the complement of A, right? So then A and B touch. Then you know that the Hilbert space is not really a tensor factorization of HA with HB. And there's various ways to say why that's the case. But the best way is just to say, well, the entanglement entropy of all the states that you think of in quantum field theory are actually infinite. So that means that there's no state which is like pure state on A, pure state on B, which means that there can't be this tensor factorization. Now, but if we allow a gap between A and B, so a little gap, we just allow for a little gap, which I'll call epsilon, then there's some sense that in theories that satisfy the split property, you do have a tensor factorization like this. And the sense is not exactly, it's not like you have this Hilbert space HA tensor HB. The way you describe it is you say, well, I have some state on B, which maybe you can think of as a density matrix on B. What you should really think of a state on B as a linear functional from operators in B to numbers. And let's say I have some state on, some state on B like that, and I have some state on A, so row B1 and row A2, and they're independent, they're not at all related to each other. The question is, can I find a state in the Hilbert space which looks like row B1 over here and row A2 over here? And turns out you can't do that in the original case without this little corridor, but you can do that in theories that obey the split property. You can always find a state on the larger Hilbert space that has this independence. Sometimes this is called statistical independence. Okay, so that's one way to describe the split property, maybe not totally intuitive. There's another way, I guess I'll get to in a little bit, which is even less intuitive. But to describe it, I have to say a little bit more about the algebraic approach to entropy and quantum field theory. So instead of thinking about these space-like regions on some time slice and thinking about Hilbert spaces, let's think about in terms of algebras of operators. Okay, so we think about regions being determined by an algebra of operators. Now, the algebra of operators should be some causally complete region, essentially because I can describe an operator in the future of this diamond, for example, by operators on this time slice, just using sort of Hamiltonian evolution, and by causality, it should be just determined by operators on the time slice. So that means, it's reasonable just to think about all the operators in some causal diamond. And so associated to all of the operators in some causal diamond, you have some algebra. And that's what I'm going to think of as my regions A and B. And instead of thinking about some Hilbert spaces, I'll think about these algebra of operators. These algebras are quite complicated, and you can show from some basic assumptions that they can't arise as, they can't be described as bounded operators on some Hilbert space. So this is a way of saying a much more fancy way of saying that is that they're type 3 Von-Neumann algebras, as opposed to type 1 Von-Neumann algebras, which are the nice ones, which come from sort of bounded operator on Hilbert spaces. And in particular, type 3 Von-Neumann algebras don't have a notion of a trace, there's no density matrices, and so they have infinite entropy. And so that's consistent with what we just said, and it's also consistent with what we know about entanglement entropy in the continuum limit. Okay, so okay, but now we're going to think about this split property. So we're going to have these A and B regions, which are these causal diamonds, and they're separated from each other by this little corridor epsilon. So now let's define the commutant of some algebra. So the commutant is just the set of operators that commute with it on the full quantum field theory Hilbert space that commute with the original operators A, B. So you can think of it as everything that's space-like separated to one of these causal diamonds, or all operators that are space-like separated to these causal diamonds, because those are the operators that commute. So in this case, I'm taking AB commutant, the commutant of AB, and just by causality, because these were originally space-like separated, these two diamonds, when I take the commutant, it means that AA has to be contained in AB commutant, the commutant of AB. It turns out that the split property then guarantees that in between this inclusion of algebras, this subalgebra, you can always find a nice algebra, a type 1 factor. And a type 1 factor means it comes from bounded operators on a Hilbert space. So, it means that you can define an entropy. You can define a Von-Neumann entropy. It can be finite. It may may not be finite, but can be finite, as opposed to the type 3 case where it's always infinite. So this n that lives in between this inclusion is nice. Okay? And so the split property gives you this. And you know, I don't claim to have a great intuitive picture of n, but I think if our conjecture is true, that I'll come to in a little bit, then you can start to try to develop a picture of that using ADS-CFT, for example. So it turns out that there's sort of, you can have many of these type 1 factors. It's a lot like a purification. You can just act with unitaries and get another type 1 factor. But it turns out there's a special one. There's a canonical one, and this canonicalness is very much related to the canonicalness of the state that I was talking about before. So there's a canonical type 1 factor that was described by these authors Doppler and Longo some time ago. And our conjecture is that the reflected entropy, AB, or the entanglement wedge cross-section in ADS-CFT, is computing the Von-Neumann entropy of the reduced density matrix on this type 1 factor, this specific type 1 factor. Okay. So why do we say that? Well, the evidence is admittedly a little weak. There's essentially an analogy that we can develop. So in the first part of this talk, I was talking about finite dimensional Hilbert spaces and very nice things, but you should think of that as an approximation to the reality in quantum field theory, where you have these more complicated type 3 settings. But in that approximation, you can see things that look a little bit like the split property. And so, for example, if we think about the Hilbert spaces we were working with in this doubled Hilbert space, AB, A star, B star, and we think about operators on that Hilbert space. So, as I said, you should think about the algebra of operators, and it's best to think about bounded operators. Then we can describe the following set of inclusions, which looks like the split property, where we have bounded operators on HA is contained in bounded operators on HAA star. That containment is just trivial, which is then contained in bounded operators of HAA star B star, which is all of the operators that commute with bounded operators on HB. So if you look at that equation, it looks a little bit like AA is contained in N, is contained in AB prime. Okay. Where here I'm identifying N with bounded operators on HAA star. And so, with that identification comes the relation between the Von-Neumann entropy of N and the reflected entropy. Of course, this is just an analogy. It's a little bit better than that. The canonical choice of Doppler and Longo it comes from essentially this density matrix has, let me say it that way, the density matrix has some symmetry, extra symmetry constraint. It's fixed by some particular CPT operator. You can take that CPT operator and guess what it might look like in our Hilbert space of this canonical purification. And indeed, rho AA star is also fixed by that symmetry. And in Doppler and Longo's paper, that is enough to uniquely specify this factor. So that's pretty good evidence. Okay, and then the final thing to say is that the entanglement wedge cross-section, right, in this setting where A and B were disjoint, is some surface that never reaches the boundary. So it's always a finite quantity. Okay, and so that finiteness I'm identifying with the supposed finiteness of the entropy of the this type 1 factor. Okay, so that's the idea for the split property. You can go a little bit further with this and say, well, maybe this is a way to think about how to regulate entanglement entropy in quantum field theory. So the idea is to think about some region A and then sort of to split it into 2 regions with some corridor, A minus A plus. And so I didn't write the reference, but if you know anything about the mutual information regulator, it's the same idea. The mutual information regulator of Cassini et al. But now, if we use the split property, we have some algebra in the inside A minus. It's contained in the commutant of A prime A plus, and living in between there is some type 1 factor, some canonical type 1 factor. And then let's just define the regulated entropy as the Von-Neumann entropy of that type 1 factor, and let me add a 1/2 there. So that's I put in a 1/2. And the reason I put in the 1/2 is because now I know how to calculate the right-hand side using this conjecture duality with a reflected entropy. And if I want to get consistent results of a regulator of entanglement entropy, then because of the entanglement wedge, in this case, so here's a picture of what's going on in ADS, and the entanglement wedge cross-section is this blue curve, but you always get twice the blue curve. The blue curve looks like the RT surface of the A region, at least it is an approximation to the RT surface of the A region, up to small corrections from epsilon. So we think of that as a regulator of the entanglement entropy. But we need this factor of 1/2 because the entanglement wedge is counted twice. It turns out that there were previous conjectures relating, for thinking about trying to regulate entanglement with this type 1 factor. So this is not really new. The new thing is the computability in ADS-CFT. So for example, that let us put this 1/2 factor in, which was not actually discussed in previous literature, as far as I can tell. But this 1/2 is also a little bit awkward because you would like to have a regulator of entanglement entropy where the answer is entanglement entropy itself. The mutual information regulator doesn't do that. This almost does it, except for the 1/2. Okay. All right. So in conclusion, we've given evidence for a new a new element in the ADS-CFT dictionary, which is this duality between this reflected entropy and this entanglement wedge cross section. There's an intriguing relation to the split property. Hopefully, that duality can be established more rigorously, and then maybe we can learn more about the split property. For example, it wasn't known previously that the Von-Neumann entropy of this type 1 factor was even finite. It's not guaranteed that it's finite. But if this conjecture is true, then it should be. And this suggests a new regulator for an entanglement. And, yeah. Okay, so let me end there and see if anyone still listening has questions.
Thanks a lot, Tom.
Okay.
If anyone has questions, feel free to ask them.
Yeah, we have a question here.
Hi, Tom. This is Eric again.
Hi, Eric.
So I was a little confused about your split property, the theorem that Doppler and Logo proved. So can you go back to that slide? Yes. So is it true that the algebra on the left is actually
I can't. Sorry, I couldn't hear.
first algebra, which you call the A of A, is that a type 3 algebra?
Yeah.
And then it's a subfactor of a type 1 algebra?
Mm-hmm.
Because you say the type 1 algebra can be represented as bounded operators on a Hilbert space.
Yeah.
While the first one cannot. So how can that be a subfactor? How can it be contained?
So how can AA be a subfactor of bounded operators in a Hilbert space? Is that the question? Sorry.
So I thought that N can be represented as bounded operators on a Hilbert space.
Yeah.
AA cannot.
That's right. Yeah.
But still AA is contained in N.
That's right. Yeah.
I
So that
difficulty to understand that. Because if AA is part of N, why can't then AA not be represented? Or is it another Hilbert space?
well, I mean, this containment is just like in quantum field theory. So in quantum field theory, we have a Hilbert space, right? And that's a Hilbert space for the full quantum field theory. and there's a set of operators on that Hilbert space which are actually bounded operators on the Hilbert space. So if I took the full region to be my algebra of everything, then it would be a type 1 factor. And then all of the sub regions that we talk about are type 3 factors. So in fact, there are many examples like this. So it can be represented as a subalgebra of bounded operators on a Hilbert space, but it can't be itself bounded operators on a Hilbert space.
Any other questions?
Yeah, Tom?
Yes.
Can you briefly explain the construction of this N of psi, and does it have a holographic interpretation, or does it mean anything in agency of T?
Well, yeah. So yeah, maybe I didn't. Yeah, I didn't really. Can you see my board? Yeah, I think that the picture that you should have in mind. I should have drawn this. I don't know if anyone can see my board. You see that? So I think here is a.
Click on the video.
Click here.
Yeah.
Can you see that? Or should I do something? Maybe I can do something. New share.
It's okay here.
I can see your board.
Okay, good. So you have A and B here. So I said that you should think of HAA star, bounded operators on HAA star, as being this N factor. And so if I think about this gluing construction, I take the entanglement wedge and I glue it to the mirror on the back here. So I have A star. And somehow, because I've glued this together, I sort of get a closed region on the boundary. And so that seems to be regulating the UV divergences that might have otherwise happened here. Of course, I'm gluing with this reflected boundary condition. But it looks like I have A star here, and then this is the Hilbert space associated to HAA star, and then all the operators on here are some type 1 factor. So it looks like this looks like a wormhole, and it looks like we're just constructing just a CFT that lives on a circle essentially. And that should have. It's not really this. It's not. The state here is a little bit funny. It's not the vacuum state at all. But I think you can think about the algebra in terms of this. And so that seems to be the picture of this construction. It's this gluing thing that you take A and you're essentially gluing it to itself or its CPT conjugate, and when you do that on the boundary, it somehow regulates the divergence at the boundary.
All right, thanks.
Sure.
So I have a question here in Potsdam. So to what extent did you test the relation between entanglement of purification and the entanglement of these minimal purifications? So
yeah.
There's this factor of 2, right? Like
yeah.
Can you say something about it?
Well, sort of. I mean, so I think this is not in the paper. This seems to be true. Well, actually, it's hard to. It seems like there should be some kind of a bound. I think this might be true. This might be true. The entanglement entropy of some purification with alpha, say some purification. This is something that would go into the entanglement of purification. You would minimize over all of this. But for some given thing, there should be some bound like this. This is bigger than 1/2 times the, can you see that? The reflected entropy. So this reflected entropy, AB. So that would give some hint as to the relation between these two, because at least there's a bound. So maybe you can try to saturate this bound. So this bound then, if I then, if then I minimize over all possible purifications, would tell you that EP is bigger than 1/2 SR. Okay, and then it's just a question of whether you can saturate that. And we haven't shown this bound, but you can again show it for the Renyi entropies. So there's a Renyi version of all of these things, and you can actually prove that for the Renyi version. So I don't know. It's very hard to extend this to the non-Renyi version. I was hoping to try to do that, but haven't managed. But I mean, this is a hint as to the relation between the two, I think.
And did you guys look at this relation in the realm of Gaussian states, or? In
Gaussian states?
Realm of Gaussian states, yeah.
Oh, you mean for some particular boundary in the boundary? Yeah, I mean, yeah, we've tried to like violate this bound, for example. You conjecture that bound, let's try to violate it. Like when n is not, when this is the entanglement, and we haven't managed to.
Okay.
But yeah, I don't know whether that was a comprehensive. We also try to violate this monotonicity bound that I told you about, and we haven't managed to. But we also don't have a proof. So.
Okay, thanks.
Sure.
Other questions? No? Okay. If there's no other questions, then let's thank Tom again for this very interesting talk. Thank you.
Thanks for setting